Hello again, class. As you can see, we're going to start our second video today on page 41. And now this we did not do in class. So the way that things are going to change here is that we're going to be rotating about a vertical axis. And that means that all of our functions now need to be in terms of y. Okay, so disk washer method with a vertical axis means everything needs to be in terms of y. So let's draw our first picture here. So we're going to find the volume of the solid obtained by rotating the region bounded by y equals ln x, y equals 1, y equals 2, and x equals 0, which is really just the y-axis itself, about the y-axis. So let's see what this looks like. So we're going to get something like, let's try that again. Something like this, okay? As we know, the graph of natural log does something like this, and I guess this would technically be x equals 1 here, okay? And now what we're going to do is we're going to take the line y equals 1, which is, let's say, this line here, the line y equals 2, which is, let's say, this line here. So let's say this is at height 2, this is at height 1. And bear with the drawing, please. And so we see here, this is the region we're going to be rotating about the y-axis. So, all right, so let's switch over to, let's say, red. When we spin this, we're going to get something that, kind of looks like this, like we're going to have this part, and then it'll kind of go like this, like so. And, we'll get a solid from this. Right. Okay, and now we're going to have a cross-sectional disk here. Hopefully the picture is clear, but we get a cross-sectional disk here, and switching over to blue, if we pick a y value now in this range, 1 to 2, so let's say this is our y value here, we need to know the radius of this disk, which is essentially that length there. And just using what we knew from page 40 from the last video, this is going to be exactly given by the height of the function. But now the height of the function, it needs to be a function of y. So we go back over here, and it looks like our function is given by natural log, but in reality, we need to take this and express it now as a function of y. So if y equals ln of x, if I just do e on both sides, I get x equals e to the y. Okay? All right. So that means now that our radius is given by the function e to the y. So now what we can do is we can form an area function. So a of y equals, well, it's always pi times r squared. And again, color coordinating here. The height of the function, the radius, are going to be the same thing for this problem. So we get e to the y. And when you simplify this, e to the y squared is e to the y times e to the y, which is e to the 2y. So you get pi e to the 2y. Whoop. Okay. Well, now to find the volume of this solid, we're just going to integrate the area function from its y. Now everything is in terms of y class, so y bounds. So we go from 1 to 2, a of y, dy, a of y, I'll save some imaginary ink again and say that this is pi e to the 2y dy. Okay. If we remember our antiderivative rules, this is e to the kx, so its antiderivative is 1 over k e to the kx. And taking account that pi there, it looks like we're going to get pi over 2 e to the 2y from 1 to 2. And working this out, plugging in 2, we get pi over 2 times e to the 4 minus pi over 2, now just plug in 1 and you get e to the second. And honestly, that's about as much as you can do with this problem. So that one's done. Okay, scrolling down now here, we're going to graph. Now you'll notice this is already in terms of y. This is already a function of y for us, so that's good. So all we need to do is actually figure out how to graph this, and then find the region that's being bounded by all of these curves here. X equals 0, which is the y-axis itself, and y equals 9, which is a horizontal line at 9. So let's see what we get. So we're going to graph this. X equals 2 times the square root of y. Well, you can make a little table of values if you like, and I may do that here just to kind of show you what we get. Now y is independent and x will depend on y. So like if if y is 0, I get x equals 0, since you get 2 times the square root of 0. If y is 1, I get x equals 2 times root 1 is 2. And let's say y is, I don't know, how about 4? Just trying to make it easy for myself here. I get 2 times root 4, which is 4. And now if y is all the way up at 9, then I get 2 times root 9, which is 6 for my x value. And so this will go all the way to x equals 6, and up here at y equals 9 is where we stop. This is like our upper line here, and so we actually have a point right here on the graph. And it's actually going to be essentially a parabola shape, but only the right half of it. So it's going to look like this. And let's see, x equals 0 is the y-axis, y equals 9 is this line here, and the curve right here is 2 root y, so this is the region we're rotating about the y-axis. Okay, and so switching colors as we do, let's see, we're going to get something that goes like this. And for a cross-sectional disk, we see the following. All right, so pick a y value in this vertical span now, in the y range, 0 to 9. What we need to know is the radius of this cross-sectional disk, which is exactly the, in air quotes, height of the function, which is given by 2 root y. Right? So our area function, a of y, will be pi times r squared, and our radius, like I just said, is the function itself, so 2 root y. And so this simplifies to pi times 4y, which I will write as 4 pi y. All right, so now the volume of our solid here, solid of revolution as it's called, is the integral over the y bounds of the region, so 0 to 9, a of y dy, which is 4 pi y dy. And integrating this, we get y squared over 2. The 2 will cancel with that 4 to give 2 pi y squared, I believe. And this goes from 0 to 9. And we plug in 9, we get 2 pi 9 squared minus parentheses, plugging in 0. Okay, everything goes away here. So 9 squared is 81, and multiply that by 2 pi, I think we get 162 pi. Okay, in the next video, we'll be starting on page 42, which should be a review again, since we'll be covering essentially the area of an annulus and doing what's known as washer method. So far this has just been disk method. There's only been one quote-unquote outer radius, but we'll be getting into outer and inner radii in the next video.